Inbar Seroussi for coming to visit us from the university. He's a professor there. He's been before in Weizmann, McGill, Weizmann, Tel Aviv, Weizmann, Technion, whatever. Nearly any university except ours in Israel. Yeah, now she's coming to visit us, so thank you.
All right, thank you very much for the invitation. I just want to say that I was witnessing what happened before, and I think it's a great idea. So what I'm going to talk about today, after this nice introduction, so I will present a theory for high-dimensional SGD, and I will show some application of this theory, and there is many, many more than what I could really squeeze into this talk. I just want to give you the gist of what we can do. So this is a joint work with many people. It's Elizabeth, Viconia, Andrew, Simone, Malco, Courtney, and Elliot. Let me start. Now, so just with the introduction to the whole idea, so I'm thinking about optimization in the era of deep learning and what I would call modern machine learning. So, as you all know, state-of-the-art models now works with billions of parameters, and these numbers are actually not up to date. I think every day it's growing, and so kind of the main goal in this talk is trying to understand how can we actually understand optimization in these regimes, and what does it mean even for models to generalize in this setting. So just to set up some notation, so I will think about supervised learning problem, in which AI will be my features or image or whatever you want to think about it, and YI will be a set of labels, and that will be my data. And in most optimization problems, you typically want to minimize some sums of functions, and you want to optimize over certain parameters, where X with my parameters is usually a very, very large vector. It would be the same order of magnitude in terms of trillions of parameters. So the main problem here is that both the number of samples and the dimension of the parameter that we are optimizing over are very, very large. So in this setting, is it clear that we actually converge to the true distribution of the data? Are we actually doing minimization with respect to the true object that we really want? So that's kind of a question. And what does it actually mean in terms of are we overfitting, or how large an N D should be? So these are questions that I think within the community are not that clear. So what I will show in this talk is that for a certain setting, we can provide exact prediction of the population dynamics of stochastic optimization method. In particular, what I will show is that as the dimension of the vector grows, actually we can show our prediction become more and more exact. This is an example of one of the problems that we worked on, and as you can see, this is the learning curve of SGD, stochastic gradient descent, with respect to the population error. So you can see that our prediction get better as the dimension grows. So I will show that on some key examples in learning theory, and I will provide some theoretical guarantees and some understanding of the optimization process. And then I will focus on some applications. So one of them will be to study also stochastic adaptive algorithms. And I will present also a new application if I will have time. But please feel free to ask me questions during the talk, so I don't have to finish everything. About differential privacy. And I will not talk about Gaussian mixture model, but if you are interested, you can contact me later.
Can I ask a question about the graph?
Yes.
The population risk is on training data or on general.
On the true distribution, yes.
Okay.
Yes. Okay, so just to set up the notation, even though I saw you already had it before. So what I will be talking about is stochastic gradient descent. I will look at the online version of it, even though the theory can go beyond that, but I will not talk about that in this talk. So what does that mean? It means that at every iteration, basically I'm taking a new example and I'm throwing it away. That's kind of thinking about, like, I have like many examples, which is something what we typically have in this era. And gamma k will be here my learning rate. And I will think about this high dimensional limit as I kind of motivated when the number of samples and the number of dimension will be of the same order. So these will be parameters and n will be samples or iteration in this setting. Okay? Okay, and so stochastic gradient descent is like an algorithm that we already know from, I think, from the 50s by the seminar work of Robinson and Ross. So what new can I say about that? So we know that in finite, when the number of dimensions is finite, then actually if you take the learning rate to be decreasing and taking it to 0, then actually you have a large number, and you can show that you actually converge to the true population. So basically this is an equation known as gradient, basically gradient flow, what people call it in the literature. What am I actually talking about? My focus will be in what happened in high dimension when actually taking the learning rate to 0 doesn't really make sense. Because if you take the learning rate to 0 and you have like trillions of parameters and trillions of examples, it will take you like the edge of the universe time to converge to something. So we will think about fixed learning rate.
But isn't that true also in the finite dimension case? Also in finite dimension, if the learning rate goes to 0, the number
that's true. That's
the graph.
slow.
well, it's a matter of, I mean, you can split it into like what do you mean by in the mathematical sense of it and what do you mean in the practical sense of it. But in my setting, like I will never think about the situation in which the learning rate really. I'm thinking about a fixed learning rate, and what is I think about going to be large is the dimension of the problem and the number of samples. And then, like, you could ask yourself, okay, what would be the limiting equation in that case? And we will try to answer this question. So I cannot answer this question in a full generality as it's been done here, so because like the set of distribution that we have here and like understanding this problem for all distribution is really hard. But I can answer it for certain distributions in the data. And that's what we will do today. And for that, I will focus on a certain branch, which is actually very large. So what I'm thinking about is that imagine that you are like some oracle or something, depending on the community you are. So some people will call it teacher, some people will call it oracle. But you generate your data. So there is like some unknown function p. And some vector x star that I don't know. And you basically do projection of your feature into this into this low dimensional space. So x star will be a matrix which will have one dimension L star and the other dimension D. And basically x star and phi are not known, but L star, I know that L star is much smaller than B. So I'm doing all these low dimensional projections. And you could add noise in the way you want. So that's my data. And on top of that, I will assume that my features are drawn from Gaussian, but has some general covariance structure that I can also play with that. And I assume just that the operator norm is bounded, no more than that. So it could be also non-invertible and have zero eigenvalues. Okay, and now you are the student, you get this data, and you basically want to kind of infer this function or infer the vector x star. So how would you do that? So suppose you're a really great student So you basically come up with your own function g. It could be also, let's say, this funding neural network that has its one layer, and that fits into this framework. So you come up with your own vector x, which also do low-dimensional projections with some dimension L, which doesn't have to fit the dimension of the teacher L star. And you basically want to try to fit into this into the teacher. So we measure the error, which will be a distance between the function of the student and the function of the teacher. Okay? And what is nice about this model is that essentially everything can be represented in terms of these low-dimensional projections. Okay? So then I have the projection of the teacher and the projection of the student, and potentially also my noise. Okay? So up to here, any questions about the model? And I should say that these type of models can also, they are known in the literature also as the multi-index model that you mentioned before. Why multi-index? Because you have a lot of, L will be representing the number of index you have. Okay? And, all right.
Can I ask?
Yes.
Can you please on what's the meaning of L and D and L star?
So these are like well, in the context of a neural network, L would just be the number of neurons that I have in my hidden unit. You could think about logistic regression, and then that could be like certain groups that you have, like you classify into groups. But in general, it's another dimension that I have in my problem. And the advantage of it is that it's reduced it from a D that could be very large to a low dimensional space. Okay, so I will start with like, you may think that this is like, oh, this is really, really easy, but apparently that's also not that easy. So I'm just thinking about my data just drawn from like Gaussian, basically noise. So in this case, I define my SGD, so this is my SGD. And then...
Sorry, I'm still parsing what you said in the Furious answer. Can you go back to the neural net example? What you're only optimizing over the first layer? Is that the way you think of it?
For now, yes. For now, I will optimize only on the first layer. There are versions of what I can.
And the second layer is all ones.
It's all ones or fixed, whatever.
Fixed.
Yeah.
And why is this an interesting?
Why is this an interesting problem?
Yeah, why not freeze the first layer and optimize the second layer?
Well, there are a set of examples which you can find that fit with this framework. I should say that the techniques I'm using can be used to study examples in which you also train the second layer. It's just that in terms of like what we want to understand already within this setting, it's hard.
Yes.
So we will go step by step. Okay, so in terms of repeating what will be the process that I'm studying here. So this is stochastic gradient descent. And what is nice is that I can represent everything in terms of these low dimensional projection vectors. And what actually happens if you really write the dynamics, you will find out that what will matter for you most is basically the overlap between the teacher vectors and the student vectors and the norm, essentially, of your parameters. And it turns out that you can actually track just these two objects. And that's the first theorem that we showed, is that essentially we can really track them and provide an equation for them in terms of what I would define as basically the metrics of the overlap and the norm. And what is happening is that I'm changing the time. So I'm thinking about each iteration of SGD as t times d, essentially. Okay, the dimension. So it's like very large iteration. And And so instead of taking the learning rate to 0, what I will do is I will take d to be very, very large. So that's what you should think about. And so we get a deterministic equation. So this is the equation. Looks a little bit scary, but it's not that much. It's really, first term will be, need to put it here. So first term will be gradient flow term that you would have if you just did the Robinson-Monroe equation. But then you have this extra term here that appears, and this is really due to the fact that I'm taking a fixed learning rate and I'm taking this high dimensional limit. And this term has some interpretation. You can think about it in terms of like some Fisher metrics of the gradient. And you will see that it has an effect. It does affect a lot of things, and we will see that in some examples. Okay, so up to here, this is what happened for the isotropic case, and there are many, many works on that. And there is even more that I did not update in the list. But it's like on this particular case on isotropic Gaussian. For the non-isotropic case, there is not that many works. There are some works also by my collaborators, and also some work by physicists. I should say that the original work on this was done in '95 by physicists, and they actually predicted the same equation that I've shown you before, but they provide it with no proof. Okay, so I just want to say like why there is so many works on the isotropic case and not a lot on the non-isotropic case, even though, you know, it's just Gaussian, right? I'm just changing the covariance to be general. What is wrong with, why is it hard? So it turns out that if you just try to sit down and write the dynamics, what will happen is that if I've shown you before that I could write equation for the norm and the overlap, actually I will not be able to do that. And the reason for that is that if you will sit down and write it, you will find out that you will have like proliferation of terms that will have k and k squared and so on. So you cannot write a closed form dynamics. So then what can you do? So this is like a funny random matrix theory trick. Basically use an object that is called resolvent. So you can also think about it in terms of essentially projection into the eigenvectors of your matrix. And the idea is that this object has like this really nice properties that if you take a resolvent and you multiply it by a metric, by the matrix, then you get back the resolvent, and you can actually expand it to any power that you want. And basically, you can also write any polynomial of your matrix using this object. So how does that help me? So if before I tracked the norm of the overlap, what I can track now is essentially some related object. I'm just like putting inside the resultant. That's what I will do. And the same thing I will do for the overlap. And it turns out that if I'm tracking these objects, then I could get a closed form equation. And that's what we do. And so then, if I just track this object, I can get exactly all the dynamics of any function that I want within this framework of stochastic vectors. Okay. Very large set of functions, not all of them, but a lot of functions. Okay. And yes.
So, you say you know something about S of t comma z, t is the time sort of, z is this property.
It is like basically in complex length, right? So
yeah. So and then you say this is with high probability very close to, so
to the iterate of SGD. The iterate of SGD when I take exactly to this object here. Okay, so I'm thinking about, so basically this S here is really a deterministic matrix. Completely deterministic.
And what is R again? The Just the dimensions, I'm confused here.
Oh, R, yeah, it's indeed a confusing thing. X is L times D, okay, and R is D times D. It's a matrix,
It's
and then
D times D, so it's a huge matrix.
yes, it's a huge
I
matrix.
see.
Yes.
And we take the dot product
Yeah.
between
This
filters, let's say, in the first layer, but with this
and, yes.
reason.
I should say that this is more for the proof itself, but actually I will show way after that that you can actually simulate things which will be easier to do.
And this is for any Z? Z is just a
For
free
any-
parameter?
Z is basically in complex plane. And what I will do is I will take after that a contour that will encompass all my eigen values of the metric scale.
But this equation is true for any Z.
For any Z. Yes. I will show now a representation of this theorem that might be maybe easier to understand. But before that, how can I actually use it for something? So I claim that any function that I want for this problem, I can write it in terms of function of my iterate and the student iterate. And this funny representation just tells you that I'm taking inner product as the way I did it before. It's basically the standards just mean x transpose k x transpose. Sorry for this funny notation, but yeah. Or any function of p here would be, I don't know, k square or any other polynomial of k. So I claim that I can represent almost all the objects that you want in this form and basically recover anything I want. And so why is that? Is that if I look at essentially at the risk, right? So this is the object that I've shown you before originally. Then I claim that this is just a function of x times a and x times a. But these are Gaussian, so I can always, they are only I can represent them as function of their covariance, right? And the covariance are essentially exactly the object that I want. So this function is just a function of these covariances. And therefore, I can represent even the risk as just a function of these covariances with essentially polynomial of degree 1. And that will be my risk. And I can represent like this also other objects. Is it clear up to here? But if you don't like this representation and it really confuses you, so we can also write it in a different form. So this is another object that I don't know if you're also familiar with, but this is essentially a stochastic differential equation. So what is nice about this object is that the first part is basically gradient flow. So that's the first part, but then I have a noise. So this is a Brownian motion, that's a noise. That's a noise term, essentially Gaussian for each time. And it's really similar in spirit to the object that I have at the beginning, which was the Fisher matrix that I had. Okay, and what it tells me is that in every direction I'm adding just a little bit of noise. And that's when I'm looking at such functions lost and I'm getting a term that will, even though I'm just adding in each direction very little noise, when I look at the overall function, then I get actually contribution.
Wait, so what is this Fisher matrix again?
It's again, it's a function, it's again funny notation, but this is gradient of f, gradient of f transpose.
And then what is the times k mean here?
Yeah, so again I will set the dimension because
Gradient
dimension
of f
is very
size d.
okay. So this is L times L, okay, and this is and this k is in RD times d times d, and then because x I said is in R L times d, then I want, in the end, I'm getting a huge matrix, which is d times L, and this is why all the dimensions should match. Do you get what I'm saying?
Yes.
Yes.
If K is equal to identity,
If K is equal to
does this give you the standard?
yes, that will give me exactly the equation that I've shown before. Yes, it will. It's yes, you can show that.
Because if K is equal to identity you had before, it's just like uniform noise in all coordinates, no?
Yes, exactly.
That's the Langevin. Is this Langevin dynamics, but with like
Color
different
noise.
general covariance?
Yes, but the noise is colored by the interactions. Yes.
This is data dependent? Like, how should I interpret it? Like,
Okay,
is the
so
color
exactly, so I didn't
distribution
finish the
dependent or
statement.
data dependent? Or
It's
what's that?
identify the statement. So again, T is the same as the T in my ODEs. And what I'm saying is that if I take functions of this process and if I take function of my original iterative SGD, then they will be close. They will be close to one another. Okay? That's the interpretation that you should have in any function that you take of your iterative SGD, for example, the loss or distance optimality, and you take functions of this object, they will be close to one another with over one probability. Did that answer your question? Okay. Okay, and that's kind of like, sort of if I started from this, then originally we have the gradient flow. Then actually now, I have this extra noise term that appearing here. That comes from the fact that I'm taking fixed learning rate. Essentially, that's what is happening.
And if you did it in the finite dimension case, you would also have.
Yes, in principle you would also have, but you will not get exactly this term. So this is actually taking into account the fact that you and I mentioned that there are some terms that will not contribute. So it's not exactly, let's say, diffusion approximation.
It's not.
So you don't need D to be order of n, you just need it to keep growing. Right? If D
Well,
is square root of n or something like that, so
No, I do need D to be
the
over.
order of n? Why? But if it's big enough, then you can
Because
still
it's the
cancel.
iterate of this process, like T here, and K, so I basically scale my time with D. So everything needs to be proportionate to. I could take, we could push it to D log n, but that's D log D, but this is, yeah. Actually, that's a great question because, like, if you want to take, for example, the square of the, or other, like, polynomial, then you should really change the problem. So this is something also interesting. Okay, and I should say that this is like closed only on this set of functions. So the two processes themselves, if you just look at them, they will not be necessarily closed. So I'll just look at this process of this stochastic differential equation and the SGD, and look at them, it doesn't have to be. But if I look at the loss, for example, you will get this exact predictions. Okay, so up to here it was very, let's say, theoretical and not without any application. I want to give some example, maybe that will clarify a lot of things. So let's start with a really simple example of D square. Okay, so my teacher is just essentially a linear function, and the student will be just, again, a linear function. Then I could really write the risk explicitly. Everything can be written in this form. But then I could also, as I said, I can write it in terms of functions of k's. And then I can really write a deterministic equation for the risk. So this is this following equation. And these functions are just functions of the eigenvalues of k and the distance optimality at initialization. And that this is like, this equation is known, like in the mathematical literature, as a Volterra integral equation. So basically, this is a linear integral equation in the MISC, which I could completely solve. Even in both analytically and numerically, I can solve this. Okay.
So, just F. You should have this property that
If you think
some
about
directions will converge much faster than the others.
yes. Okay.
Where do we see that? in the
Oh
equation?
yes. So exactly. Okay. So that now you're touching on things that people have been looking at, and this is actually this type of equation actually have been used to study, for example, scaling laws and stuff like that. So here, if K, for example, let's say that has a spectrum that has a power law, for example, then you can see that F will behave like a power law. So then you will see that the risk will decay like some power of T, for example. And that's, I don't know, today is very hot in a sense to understand how this dynamics is affected, because that's related with some other application of this theorem, which you could think about how to reduce the set of parameters that you actually have.
But also, if K has a direction that has very small eigenvalue,
Yes.
then e to the minus would be 1.
Yeah, so
So we'll decay very slowly.
decay very slowly, exactly. Yes. Exactly.
But also part of it is buried in the gamma is also a parameter of the problem, right? That's
Well,
a
gamma is
vector.
basically gamma here is basically the learning rate. It's just a scalar for now.
Wait,
So gamma is a scalar.
so what happens to the dimension? K is a matrix, no?
K is a matrix.
So you multiply the matrix by a vector e. So e to the, I mean, we
So
have
this is
a vector and the exponent.
This is all quadratic form, right? So all this is a matrix.
This is e to the matrix. It's a matrix.
Yeah.
It's
Okay. Yeah, it's a major, it's not, okay.
Yeah. It's
We
a
had
matrix.
Zohar last week, so we're all set with physicist notations.
Yes, I was counting on that.
So if this is a diagonal matrix, you just
Okay.
exponentiate
Yeah.
every one of the eigenvalues.
Yes, exactly. But this is just a quadratic form. You could just think about it as a vector, a x transpose matrix K, x. Okay? And my matrix is, here the matrix is basically K times e to the minus some matrix. But yeah, that's basically what I have here. And you could express it also in terms of the eigenvalue of the matrix. Essentially, that's the only thing. Okay, I'll touch on that in a second. But this is good questions. The other question that you asked me about L, so you could think about the situation of logistic regression in which you have, like, let's say, C classes that would be L, for example, and then like G would be essentially the softmax. And in this situation, well, we want to, the loss would be the cross-centric. And actually that's the picture that I've shown you at the beginning, and it has a really explicit formula that we can really write and show and solve exactly. So this is the curve that I've shown at the beginning. And another, so up to here I show you just.
So can you go back and that? What is the x-axis and the y-axis? This is the iterations.
Oh, this is the y-axis is the population loss, and the
Which you can calculate. You don't use a test set. You can calculate it mathematically.
Yeah, I have a formula. Here it is. This is the
Where is it?
formula. And this is the formula. It's an exact formula that I can calculate.
Because it's a teacher.
Yeah. It's an explicit formula. And the y and the x-axis is the iteration of SGD divided by d.
And so the shape of the
this
particular
curve.
shape of the way the loss is going down is something that you can predict.
Yes. I could predict, and when we actually do that, we can provide asymptotics of these curves. Yes.
And what is it? What is that shape? It's not a parallel, is it? It's not...
Well, okay, so this is touching on other things, but depending on, this is where the structure of the covariance matrix comes in. So if you would put covariance matrix that has a formula, then
this would also
yeah. Actually, for logistic, even if you don't put, you can get 1/2. But this is if your matrix is lowering. So this is something else we can discuss.
So the interpretation is that it sort of learns the directions sort of one by one. So as I go in time, I learn lower and lower eigenvalue corresponding directions.
That's a good question. I'm not sure that that's exactly what happened in terms of the directions. Yeah, I don't know. I don't know if I would say it like that. Let me show you another example, and maybe that's clarified, because all these examples are sort of like convex situation, but we can also touch on things that are not convex. And maybe the most canonical example for that would be phase retrieval. So this is so what I'm doing with phase retrieval is that my student is basically the absolute value of some vector, projection on A, and the same thing is here. And you could think about, you have a Fourier, basically the Fourier image, and you want to infer the phase essentially of your image. And for mathematically, I don't have all the information to infer the exact direction of that stuff. But I want to, with enough example, I want to do that. So here something kind of funny happens. So it's really important how you initialize. Okay? So it turns out, because the problem is non-convex, that if you start with some just random initialization, then you really, if you want to project it on your true vector x star, then because you're in I dimension, you have two vectors in dimension d, and you take the overlap between them, then it's 1/square root of d. So, and d is very large, so the overlap goes to 0. Okay? So that means that I start the optimization already with 0, and it takes me a lot of time to build up this overlap. And this is exactly what happened. So it actually takes d log d iteration for SGD to converge. But actually, if you give it some warm stuff, this is what people have been done in the literature a lot. So kind of telling something about the direction of x star, typically spectral information, then you can actually recover it in the iteration. And what you see here is basically what we plot is, I look at the overlap as a function of the norm, normalized norm of the student divided by the norm of the teacher. And this is for different values of the learning rate. And you can see that if I look at a very small learning rate, which corresponds to gradient flow, it takes me a lot of time to build up essentially the overlap, and then the norm, and then the overlap essentially. But if I increase the learning rate, then I do it faster. And also, you can also see it if you just look at the loss. So this is an example of the loss. So at the beginning, there is this descent phase. I decrease very fast, but then I kind of stuck in some saddle point. And it takes me some time to get out of it, out there. And that's actually depend on my learning rate. So if I increase my learning rate, at some point, I will be able to do it faster. So this is what happened for larger learning rates. And this is also, I think, noted in the literature. Maybe you heard this term of edge of stability. So for this, for stochastic gradient descent, or essentially for optimization, that kind of shows that working with fixed learning rate, we're actually working in really close to the threshold of stability of the algorithm. And this is actually the regime in which we actually generally work the best. And this is also what you see essentially here. Okay, so I talked about stability, so let's understand a little bit more what's going on with stability. So this is more like an optimization problem. So what the learning rate will ensure that I will be descending. So I'm looking at the distance to optimality, or like the distance between my teacher and my student. And based on my theorem, I know that this is converging to a deterministic limit. And I really have explicit equation that describe how that converge. So that gives me some dynamical threshold on my learning rate. But what is important about this threshold is that it depends on the average eigenvalue of my covariance matrix. So that's important. So if I assume what typically has been assumed in optimization, I assume that everything is convex and smooth, then actually I can get a constant threshold, but still depending on the average eigenvalue. And essentially, this is kind of different than what you will find in classical optimization, which everywhere it's divided by the largest eigenvalue. So that shows you actually why actually we can push to a larger learning rate, and that is important for when you are in high dimension.
And why intuitively is it like I can always just pack more meaningless dimensions, and it shouldn't matter, but it affects the average. So like how?
It's only because you're in high dimension, because if you're in fixed dimension, the difference between average eigenvalue and the largest eigenvalue is not that large as if you're like in high dimension.
No, but intuitively, why does anything depend on average eigenvalue? If I can always, for any problem you come up with, I can just come up with another problem that just has many, many more dimensions that are nearly meaningless. The average will be affected significantly. The optimization I would expect would not be affected. So why is average indeed what matters?
Why is the average indeed what matters?
Intuitively, not the math I trust, but like, it's really surprising because like.
I think, well, in terms of, I think it's like, maybe I should rephrase the question differently. Why is the largest eigenvalue not affecting here? That's okay. Like kind of the other, the more and I think that because you're in the end, what you're looking at is always functions of average of these objects, and you're never fixing on particular direction. This is my intuition. So this is why in the end that the average of the eigenvalues will appear. And that's actually what happened to you in practice in this high-dimensional setting. Or in general, most of your function will be a function of these quadratic forms. So looking only at the largest eigenvalue is not the right object. And the same thing if you just look at the convergence rate. It will depend on some sort of average condition number. Okay. And we actually also see that from the simulation. So if you look at the distance to optimality as a function of the learning rate, and here what I did is that we look at different spectrum of the covariance structure. So basically this is a way to generate some parallel spectrum. Magenta pastor is basically what you will have if you're taking a covariance matrix that has Gaussian entries. And we normalize all of them to have fixed average eigenvalues. And what you can see is that we change here the power, and it actually didn't change the threshold of stability. They all collapse on the same point. And this is exactly the reason, because we had the same average for all of them. But you see that the convergence rate did change. So the distance of optimality was actually was stable up to this point. And this is kind of just to see the theorem in a simulation. Okay. All right. So now, do you have more questions on this part before I move to adaptive algorithms? It will be more of the same, but kind of extending this to more.
I'm still puzzled by Moshe's question. Can you?
Yeah, sure.
If the learning rate is larger than 1 over the largest eigenvalue, then you should oscillate in that direction, no?
What do you mean oscillate?
You just have a one-dimensional function,
Yeah.
and your learning rate is larger than, so you're not going to converge to the minimum, you're going to overshoot and not converge.
I think that the reason why it's like in the classical optimization it always appears the largest eigenvalue is just because in terms of bound. Like the way they bound it, they're always bounded by the largest eigenvalue, and they're always convenient. And here what we did is not provide bound, but actually provide the exact asymptotics. And when you provide the exact asymptotics, you can provide a tighter threshold on the learning rate. That's kind of, do you see what I mean?
Yeah, but I think if you just take a one-dimensional function, like a parabola,
Yeah, okay.
and you do gradient descent on it,
Yes.
with finite step size. If the step size is larger than the curvature at the minimum, you're not going to converge. You're going to
Right.
Bounce back.
Yes.
bounce back and forth. And that's usually when people talk about the largest eigenvalue, they say, if I have a quadratic function in many dimensions, if I have a finite learning rate, I want to make sure that in all the dimensions I don't overshoot and bounce back and forth. So that's why you need a learning rate that's smaller than 1 over
Yes.
the largest
Okay.
eigenvalue.
Okay. That's a good point. That's a good point.
But here somehow you've gotten rid of that, which
Yes.
is weird.
Yes.
Okay?
I'll explain why.
Okay.
The reason for that is essentially because you're always thinking about the iterate themselves, but I'm thinking about always these average functions. I'm not interested by each direction. I'm just interested in, let's say, the distance optimality or the loss, which are essentially functions of average of the iterate.
No, but
So-
in the one-dimensional example, the loss will not go to 0 either. It will just,
No, but the one exactly that. The
Okay.
one-dimensional example is if I would. I'm just saying that if you will look at your iterate, right? You have x, which is an RD. Here it's in R, but I'm looking, let's say, in RD, right? But your one-dimensional example is like you're looking at this x squared is R. It's not working. Okay. So you're looking at this x squared and you're trying to track how this object is stable. But I'm not interested in each coordinate of this one. I'm just interested in the average of this.
She rigged the game.
So-
She chose the way the loss is defined.
So I'm
forces
not
that
interested
no
in
one
one.
coordinate can matter too much.
this
Because-
means the average over all dimensions, the norm, not... Is that the point?
Yeah, and I'm always looking on average, and actually this is what is interesting for you, right? You're not interested in each particular direction, you're interested in
That
average.
depends on the structure of the loss. But
Yes.
the thing is also that right, because like if my loss
If your loss
my
is
loss is
concentrated.
arbitrary,
Yeah,
but
yeah.
the thing is you also chose the loss to be such that it's averaging over everything.
Yeah, but
Okay.
this is something that happens to you. So that's exactly the point. This is a great question. Okay. Okay. So now maybe.
So how do you do the simulations? You take D to be very large, presumably.
I mean, it doesn't have to be large. You see, well, in the example that I've shown before, it could be even 100. It would still be fine. Let's see. Where is that? The logistic regression. Here.
I see.
You see, well, even 100 is fine. It's
But presumably, even in 100, one of your directions is not converging. But but somehow,
Somehow, if I look at the average,
if you look
then
at all,
it's a-
all the average over 100
Yeah.
dimensions, it doesn't matter so much.
yeah,
Okay.
yeah. It's a sort of a flow of large number result. Yes, exactly. Okay, so to adaptive learning rate. So here the motivation for that is that, okay, I told you that for fixed learning rate we can provide this theory, but in practice finding this great fixed learning rate that will lead you to a good generalization is hard. So what people do is, as the question for everything, they learn essentially the learning rate. So and this type of method I used a lot in practice, and example of them are Adagrid, line search, Adam, Spark, the adaptation dogs, many more of this, and they're invented every day, like another method of optimization, in which, and kind of within our framework, what is changing is that this learning rate here is not just a function of data rate, but actually it's a stochastic function, because it depends all your history of gradients. So that's kind of the problem. So kind of, if before what I've used a lot is that everything was Markovian, so everything would just depend on my previous iterate. So now if I have this stochastic adaptive method, then everything depends on all my history from before, then the system is no longer Markovian. So that makes things a little bit harder. But actually it turns out that we can study that as well. And this is an example. So this is Adagrid norm. So what you see here is that how is the learning, so this is just the definition of the algorithm based on this paper. I'm just looking at the learning rate that takes into account all the history of the norm of my gradients. So that's what we do. And it turns out that we can also provide a deterministic limit for this object. And this is basically, here I'm just keeping everything with L equal 1, so everything is D. So this is my Fisher matrix from before, but it is just a scalar here. And in the case of least square, it will just be the loss. Okay, so essentially the learning rate will depend on the loss. And in particular, it will be 1 over integral of the loss. So if the loss will not be integrable, then it will go to 0. And if the loss is integrable, then it's not. And this is just pictures of how we can really predict. Even here, you see we took a really small d, and it's still converging quite well to the results of the algorithm. So this is for the learning rate, and that's for the risk. And this is for least square and logistic regression examples. And I'm going back to the equation that I've shown you for the least square. So that's basically this Volterra equation. So for Adagrid, the situation is quite simple in the sense that I could just scale time with respect to this learning rate. So you get the sort of similar equation, but a little bit more ugly, in terms of the learning rate. And it turns out that you can also analyze this one. Okay, so kind of the question here will be, is does the learning rate decays to 0 or not? And what we can show is that we can basically, by studying the learning rate, we can show different regimes. So if you do have noise in your problem, in your labels, then you can actually show that you can bound everything and the learning rate will converge to 0, and it actually will go like 1 over the square root of the iterate. But if there is no noise, it actually depends on the structure of the covariance. And we can show that if the problem is convex, and then the learning rate will go to 0, or if you have just finite number of 0 eigenvalues. So that's kind of related to the questions how the structure affects. But if it has like some powerless spectrum, then you will have some sort of phase transition in the behavior of Adagrid. So let's just work for a second with the situation of strongly convex case. So here, I think one of the surprising point was that, okay, we can actually really predict what will be the final learning rate. We have a formula. We know exactly what will be the final learning rate that the algorithm converges to. So it's this object, which is the initial learning rate at the start here, the distance to optimality. So, and again, you have this average eigenvalues that appear in here. And what's kind of like surprising here is that, or maybe actually was somehow noted by the people who do this, develop this adaptive algorithm, is that it does depend only on the distance to optimality at initialization. So kind of, if you really want algebra to converge well, you basically need to know this information about the distance to optimality in order to understand if this is actually predicted by our theory. And it doesn't really depend on the condition number, for example, of your problem.
But
Yes.
isn't the optimal solution dependent on the learning rate that is chosen during the process?
Yeah, so exactly that's the point. That's the point. So if you really want algebra to work well, then you need to know this information. That's kind of a problem for this algorithm. Okay, and so if you do have this information and you have some sort of warm start, then it will converge well. Okay, and so this is motivated by other method that try to avoid this idea, in which you have this information and sort of learn also this object. Okay, and this is the beginning of like understanding how power law affect, but there is many works that extend within our framework to study different powers of the covariance. So here you see different regimes. So depending, so this I would just say that these conditions have been like studied in many works, and they typically are being called source capacity conditions. So it basically says that lambda here is the eigenvector values, and omega I are eigenvectors of my covariance matrix, and I'm just putting them in, doing a histogram of them, and the histogram has like power law behavior, and this is projection of my true XR with respect to the eigenvector of my covariance matrix, and I assume that there is some sort of localizations. So these type of conditions are known as source capacity conditions, and if we put them into our problem, we can show that we have different regimes for other ones. So these are the three regimes that are shown here. So there is some sort of phase conditioning that is happening, and at some point you can really see that what we discussed before, that the risk can really provide an asymptotic behavior of the risk, and it does decay depending on the powers of this, and you see the slow decay. Okay. And we can also see that in simulation. So this is an example of that. Okay. So I have another, but this is depending if you want to hear that. But this is okay. So I would just say that it's another use of the theory to provide better rate for differential privacy, which I will not have time to discuss this, but the idea is kind of to understand how clipping affect in differential privacy, and we can show that actually the regime of aggressive clipping is actually can be very good in certain situations. We can provide better rate for that, and this is really using the same theory that I outlined before, but I will skip that. And if you have any questions, then please feel free to ask me. Yeah, I was pushing a little bit too much. Yes. Let's get to the end. Just give you a flashing of what we can do. Okay, so to conclude, So I showed you this exact theory to study SGD, and also adaptive learning rate. I should say that we can also study with it momentum and also multipass, so not just online gradient descent. And so we discussed this optimality condition that depend on the average eigenvalue, not the largest eigenone, the largest one. And I also presented what happens for certain adaptive algorithm and how we can study them and show exactly why essentially the distance optimality condition is important. And so this is something that I started to discuss in the end, but it's really quite hot now, is this idea of scaling laws. And that our theories really allows us to provide asymptotic behavior of the loss, and you can think about a situation in which you have a certain compute budget, and so you can actually think about how you can use this to basically try to reduce your set of parameters of the problem if you know exactly from the beginning how the loss is asymptotically big. And this is also in terms of undergrad application why certain method will be better. Okay, this is differential privacy. If you want to talk to me later. Okay. And also Gaussian mixture model, which I will not talk today, but it's another. Okay.